Hey everyone, I am Superfizz or Hank from the ETH Staker community, and we are here with the Medalla Data Challenge Submission Showcase brought to you by ETH Staker. ETH Staker is a community of users that supports staking on the new Ethereum Beacon Chain network. We'd love to have you join us sometime at reddit.com/r/ETHStaker or on our Discord at invite.gg/ETHStaker. Today, I am joined with my co-host, Michael Geeson from Helvetica, our friends from ETHStaker, Buddha and Patricio. Buddha is with Beacon Chain and Patricio is with the fantastic POAP platform. I don't know if we've mentioned yet, but we are offering POAPs for submitters to the Medalla Data Challenge, and I think that's not just the people who show up here, but we're offering to all submitters. Is that what we agreed upon, Patricio? Great, yeah. So if you're a submitter and you're watching this, we'd like to reach out to you and get you a POAP for providing a submission to that challenge. We're also joined by Danny Ryan from the Ethereum Foundation. Danny has had a recent fantastic success of getting the deposit contract for the Beacon Chain up and running. So congratulations there. And great. With that, I'd like to give you a broad overview of what we're doing today. The Medalla Data Challenge was a data visualization challenge proposed by the Ethereum Foundation. There were about 23 submissions, and ETH Staker is kind of curious. We wanted to know what those submissions look like from the submitters. So we sent a request out and got quite a bit of feedback from submitters who wanted to share with us. And so we're excited to share that with everyone today. Here we have, and actually, yep, I'm going to do my best to, let's let all of the presenters pop in really quick and say hello where they're from, because I'd like to get everyone a chance to say hello before we go on. We'll use the same popcorn style we used in prep. So Michael, if you want to say hello really quickly, and then we'll pass it on.
Yep, Michael Geeson here, also known as Helvetica.eth on the Reddit and Discord ETHStaker communities. I'm one of the moderators there.
Hi guys, Ian here, also known as Bata. I work on the Beacon Chain Explorer and spend my time on Discord in the ETHStaker community. Yeah, Patricio.
Here.
Okay, I'm Patricio. I run POAP. I do many things related to Ethereum 2, and I'm here to learn about all the submissions of the Medalla Data Challenge, and I pass it to Splunk's Knight.
Hi, I'm Nate McKervey from Splunk and online known as Data Physicist. I'll pass it to Sid.
Hey, I'm Sid. I'm part of the ETH2 data GitHub challenge, and I worked with Elias Simos on this challenge. I'd like to pass it to him.
Hey everybody, I'm Elias, and I work for Bison Trails as a protocol specialist, and worked on this submission with Sid. Passing it on to Gurdal.
Hi there, I'm an associate professor of business at UAE University in Abu Dhabi, UAE, United Arab Emirates, and we are a team, block data team, together with Joseph Kholodenko. He is a data engineer at Memorial Sloan Kettering Cancer Center. Thank you so much. Please, next, I guess, Siang.
Hi, I'm Siang from OmniAnalytics group. We submitted 2 submissions to the Medalla Data Challenge. I can pass it on to Lawrence.
Yep. So I'm Lawrence at OmniAnalytics group as well, and I'm here to support Siang. I guess we'll pass this to Anthony.
Hey, I'm Antoine. I work at Splunk with Nate. Pass it on to, I think that's it. All right.
Okay.
Thank you.
All right, great. And From there, we're ready to get started sharing submissions. What we've asked from submitters is that they take about 5 or 8 minutes to give us a broad overview of their submission. This is not going to be exhaustive. It is a supplement to the actual submission. So the intention here is to give people an easy introduction to the submission so that they can go and find out more later. So Michael.
Yep. So first up, we have presenting Siang and Lawrence from OmniAnalytics. Siang will be the one presenting. They've got 2 submissions. One is the proper proposers and skipped slots. The other is the art of slashing. So with that, I'll give it to Siang.
Hi, let me share my screen real quick. Okay. Okay. Hi, again, I'm Siang from OmniAnalytics Group with Lawrence here. And we are here just to talk a little bit about both of our submissions for the Ethereum Medalla Data Challenge. Just a little bit about me. I'm a data scientist at OmniAnalytics Group, a boutique statistical consulting firm specializing in statistical analysis, machine learning, artificial intelligence, and now cryptocurrency. I graduated from Georgia State University with a PhD in mathematics. And please join us over on Twitter at OmniAnalytics to learn more about us. Our first submission is on analyzing validator performance, titled Proper Proposer and Skip Slots, a ranking and segmentation study of validator behavior. And most of you probably heard that Ethereum 2 phase 0 gone live yesterday. We can get started on being a validator today. To participate as a validator, one needs 32 Ether to be placed into activation epoch, then wait until the first epoch it is eligible. After that, a validator will be activated and may begin to propose or attest. And you can exit voluntarily or be forced to exit. Our goal was to characterize validator behavior in order to construct some type of scoring methodology. And in order to do this, we must collect data set that acts as a representative of the various behavioral aspects of a validator. And we use data collected from the Beacon Scan blockchain explorer. Our analysis tracked the behavior of over 80,000 validators. The data consists of the following: row index, public key, index number, the current balance, the effective balance, the number of blocks assigned, executed, and skipped, the eligibility epoch, the activation epoch, the exit epoch, the withdraw epoch, and the slash indicator. Here we have a simple graph, and we can see that around 20,000 validators were activated during the Genesis block. And since then, there is a constant growth of 4 validators per epoch. However, we also notice there are 2 anomalies, one around 3,000 and another one around 14,000. In both of these instances, no validators were onboarded. These 2 small hiccups in the network just showcase that any technique that tries to characterize performance must also be aware that exogenous factors can influence validator behavior and therefore affect the analysis. To categorize the validator behavior, we use a weighted linear rank scoring algorithm. Using the current balance, number of successful execution, the active status, how long the node has been active, the number of skip assignments, and the slash indicator as inputs, we would just calculate a score using this formula shown here. It is just taking the rank of a validator along each of these variables and multiply each rank with some weights and add up all these weighted ranks to form a new rank score. Then we can then sort. Then we decided to settle it on a selection of 7 score tiers to differentiate network behavior. For instance, tier 1 is the top 3% that has a perfect track record of no skip slots and no slashing, while tier 7 is the bottom 6% who are mostly inactive and have the lowest current balance. Our tiers all possess distinct behavioral characteristics useful for discriminating between them. However, there is also a deeper level of heterogeneity that exists within the tiers themselves. Across the landscape, the scores within most tiers coalesce around one another, forming a localized region, as you can see in this graph. In tier 4 to tier 7, all have multiple regions where validator scores rest. Here we are able to highlight some validators within the data that possess representative characteristics and behavior native to each localized regions. The table here shows a representative samples of most common validator profiles within each tier. And as mentioned, there are 7 tiers, with 1 being the highest and 7 the lowest. We start with tier 1. We have our perfect proposer, a validator who exhibits the best combination of behaviors we track. These validators have the highest number of successful blocks to go along with their longer than average active time on the network. Next, we have tier 2 validators. Though they have similar characteristics as tier 1, particularly perfect proposal rates, they have been active for a slightly shorter time and have proposed fewer blocks. In tier 3, we see the trend continue where they've been on the network a shorter and shorter period of time. And tier 4 is where poor performance begins to manifest itself in actual skip blocks. We can see new validators and those who have skipped 1 or more blocks proposal in this tier. Then in tier 5 and tier 6, we start to see more and more skip blocks and lower current balance. In particular, validators in tier 6 have skipped more block assignment than they have successfully proposed. Yet, they have managed to stay on the network for a longest period of time. And lastly, we see new validator who have been slashed regardless whether they've skipped a block in tier 7. And with only a few months of data, we expect that these findings will continue to evolve, and as such, the tiers defining relative performance of validators will continue to need adjustment over time. And next is our second submission on slashing, titled The Art of Slashing. To prevent attacks on the network, a validator can be slashed and ejected from the network if found to have broken a set of rules. Slashing means that a significant part of the validator stake is removed, potentially up to the whole 32 Ether. Our analysis is based on 1751 slashings captured on beacon scan. And the variables are the row index, the epoch number that the validator was slashed, the slot number that the validator was slashed, the amount of time passed since the validator was slashed, the index of the validator who was slashed, the index of the validator who did the slashing, and why. Slashing sounds pretty scary, but the likelihood of a slashing in any one slot is actually very small. On this graph, we see one huge spike around 3,000 epoch and another around 12,500. Excluding these spikes, there's approximately 63 slashes per 1,000 epoch, which is not a lot. And among these slashings, 97% are due to attestation rule offense, and the rest are due to proposal rule offense. And note that most of the proposal rule offense occurred after 13,500 epoch. And here we have a simple distribution of the number of slashings received by a validator. So you can see most validator only get slashed once or twice. So it's very surprising that a validator was slashed 7 times, and that's the highest number where one was slashed. And similarly, a validator who have done, most validators who have only done slashing once or twice. And 8 out of these top 10 validators who have done the most slashings turned out to be in tier 3, according to our ranking system. The highest number of slashes done by a validator was actually 93. The nature of slashings allow us to visualize the slashings via directed graphs, where each node represents a validator and directed edge represents the act of slashing. And interestingly, no validator gets slashed by the same validator twice. So we have simple directed graphs. And also we have this star pattern that we can see over here on the right side. And it's also very interesting that there was no revenge slashing, and thus there is no double-headed arrow in our graphs. It's only one arrow pointing to the other. As the network of validators continues to grow, we expect the number of interesting subgraphs to grow with it and represent some interesting dynamics in terms of the interaction between validators as it pertains to slashing. And if you would like to more details on our submissions, please reference our articles. And to end this presentation, I would like to talk about what our next steps could be. We would love to automate the data collection process to create an easy to analyze data set. With improved data sourcing, we'll be able to expand the set of variables we use to characterize the performance. And finally, we're ready to create a visualization and early warning tools that would flag poor performing validators, improving the overall security of the Ethereum network. And lastly, I would like to thank the organizer for putting this together and everyone for listening. Thank you. Does anyone have any questions?
I do have one, and I always have to acknowledge it might just be my naivety. How does a validator get slashed more than one time?
Getting slashed, maybe it wasn't a huge offense, I would guess. Maybe just some small stick that is cut off, but maybe Lawrence can explain more.
Yeah, so not exactly sure why there are multiple slashings, but it kind of does make sense. I think that it's just either one violation of the attestation or the proposal. So maybe they submitted multiple blocks. Yeah, so they've been assigned to their slot, right? They submitted a block, wasn't valid. They got slashed and punished for it. And then maybe they had sufficient balance so that the balance stays high enough. So then, okay, they get a next shot at it. They propose another block, boom, they get slashed again. And so that's how they can probably accumulate multiple slashes.
Okay, I was under the apparently false impression that a slashing immediately put you in the exit queue. So I guess that's something that I will need to learn more about.
Maybe it was
right. We now need to look at what exactly is happening there, but you can only actually be slashed once. But suppose you were part of suppose you're part of an aggregate attestation that has you at attester 1 and attester 2, and then another aggregate attestation where it's you, attester 2, and attester 3. Both of those could be submit on chain, although you would only be slashed once because there was additional information in the second one. But it might depend on kind of little things like that. But ultimately, you only get slashed once.
You know what you can do, Danny? You can also look on Beacon Scan because they have the /slots. I guess that tab, and you can actually kind of verify that some of these,
I'll check it out.
Yeah, some of those validators have been slashed more than once. So even though it probably shouldn't be occurring, you can clearly see it in the data.
Okay.
I was curious about the validator tier lists because if a validator just joined recently, he will have a higher balance than a validator that has been validating since Genesis, and maybe he wasn't offline. So how does that weigh into the tier list? Did you guys calculate it in when the validator?
Yeah. Siang, can you pull up the slide really quick? Because it actually is highlighted in tier number 4. Let's see if you can bring it up. Oh,
yeah, the slides.
Yeah, could you bring it up? Yeah. Next slide. Next slide. Yeah, so your question, Buddha. So if you look at the very first one in tier 4, that's basically a brand new validator, right? So at the time, basically like 60 blocks, I think that's what it is. But they've had no executions and no skips. So they basically haven't even been assigned to anything yet. So the way the scoring ranking says that, you know what, we can't give you a high score yet because you haven't proven yourself, but we also don't want to dump you. So we throw you in the middle. We throw you in the middle of the middle tier list, which is kind of cool. Like this was actually a result that came after the fact that we were doing. Took a little bit of calibration, but after we fiddled around with the weightings, we came up with something that was really nice. So basically, you start in the middle row, and as you get better, you rise in the ranks. Pretty cool, eh?
Nice, thank you.
Yeah.
Awesome, great. And so if you will disable screen sharing, thank you so much. You guys, your submissions were very interesting. I was a little worried they would be over my head and I wouldn't be able to grasp them, but I thoroughly enjoyed that. Thank you so much.
You're welcome.
Yeah.
And so it was great. Next, we're going to move on to Nate McKervey and Antoine Toulme from Splunk. Looking forward to seeing what you guys have to share.
All right. And I assume everybody can see and hear?
Yes.
All right, great. So our goal was to bring together like a really wide variety of data and then use that to investigate, monitor, alert, act on it. And so in this case, what we did was we brought in data from 3 different clients. So we had Prism, Lighthouse, and a Teku archive node. And then each of these clients is generating multiple types of data. So we're bringing in auth logs, system logs, beacon chain logs, validator logs, as well as system metrics like CPU, network, and disk. And then we used a couple different methods for data regarding nodes that we didn't have access to or full access to. So for example, we're scraping ETH2 stats, and that provides data on like version, heads, sync stats, memory usage, peer count, and for Prism and Lodestar attestations. But not all nodes are exposing this data because it's an optional flag. So to get more data, we customize chainD to send data to Splunk instead of a database. And so this gets information from the beacon nodes, including proposer duties, beacon commits, validator blocks, and blocks, which those blocks include like the structure, the attestations, proper proposer slashings, attester slashings, and voluntary exits. So there's a lot of data there. But then we also added the Splunk Connect for Ethereum, which is an open source connector for getting data from ledger and nodes. And on this case, we were getting data from the Gurdal network, including blocks, transactions, events, and metrics. And the nice thing here is that this little connector will also deserialize transaction events if it's given in a contract ABI. And then it also performs contract fingerprinting to match the ABIs with function signatures, and then automatically decodes the parameter names as well. And then there's a bunch of other data sources that aren't listed here, like from Discord data and so on. But the TLDR is that there's a lot of different types of data that when you combine together can create really rich analytics. And so what we did was we created this operations center, which provides a high level overview of a bunch of stuff. And then each one of these areas, you can drill down into other dashboards or the raw data itself based on whatever's interesting to you. Now, I set the time range for most of these dashboards to around the October 13th timeframe, since it was a time period where things started getting interesting regarding the health of the Medalla Testnet when it began to degrade a bit. But note that all of this data is actually streaming in real time. So these dashboards, if I set them to real time, would be animated. There's no need to scrape data, put it in an CSV, and then analyze that static data set. This is all real time. And so at the top, we see just some basic statistics across the board. We can even see like the top graffiti here. So this is, some of that automatically converting like the input hex into something that's human readable. So if you're trying to earn POAP, you'll actually see the POAP information here, but that's not really useful for health. All the other stuff is more useful for health. And so this health score is calculated from a combination of the health of many other scores. Think like Gini coefficients, online validators, a bunch of other stuff. And so pretty much everything drills down. So let's go ahead and take a look at a few of these, starting with like the address explorer. And so this is just a basic dashboard just showing like the addresses, the total transactions in the last 24 hours, a lot of 32 ETH going to the deposit address, which is what you would expect. And then we can see that you can do like real-time force directed stuff. So a lot of people are sending to this contract address, but then we can go and do like second level relationships. What happens after that? The thicker the lines, the more ETH that's being sent. And all of these, you can drill down into the raw data itself. So this is the actual data from the ledger. And this is coming from Splunk Connect for Ethereum. So you can actually connect it to multiple networks. Instead of going to a different block explorer for each network, you can just send it all into one place and search across it. So I could send DAI to the XDAI network and search one address, and I'll see the transaction across layer 1 and layer 2. Or you can connect to ETH1 and ETH2 and search across them. So I just put in the ETH2 deposit address, and we'll just search for the number of transactions the last 24 hours. And there's been, 1,752 events with a bunch of different fields. And you can see that the majority of the deposits are 32 ETH, but there's other stuff going on. And so if we go back to like the lower left quadrant here, you'll see like a version of ETH2 stats that we recreated and enhanced a little bit. So we can see all the different types of client types, how many nodes are online, the versions of those nodes, are they syncing or not? Remember, this is from, I think, October 13th. Yeah. And you can see the locations of these nodes. And if some of them are having issues, they'll show that they're offline. And then you can see various information about them that's being exposed, the number of peers, the history, attestation history. And this was kind of useful because even my node, one of my nodes, I was running Prism node and it started having issues. And I was able to debug it because we're bringing in all that data, and I could see all the errors and warnings and what the root cause was. It turned out it was a bug that was introduced in the Alpha 29 release, which I upgraded around October 13th. And so did a lot of other people. And the Alpha 28 went down and Alpha 29 went up. And the Prismatic Labs people made a hot fix, and it fixed the issue, but most people waited. Everybody knows the story, I think, by now. So it was kind of cool because what happened was I saw that even when I upgraded and tried to get my node back online, I ran out of memory. And then I just increased my VM and then it started working again. But it was nice to have all those logs in one place. And so then we thought it might be useful to show the memory usage by the different versions of the different clients. And you can see like which releases are using less memory and a bunch of other stuff. And then you can do slashing analytics too. So we can see who's been slashed the most. And since a lot of people are requesting Gorilla ETH on Discord, we just do an export of the addresses people are requesting with their username. And then you can start to associate who is doing what. And you could combine this in force directed graphs to really get a lot of neat information And the slashing information, you could also do force directed live in real time. And we did a lot of Gini and Lorentz stuff too. So we want this obviously to be as close to 0 as possible, the Gini coefficient. So we have the most even, I guess, distribution. Everyone's probably pretty aware that there's a lot of Prism nodes out there. And if there's an issue with this, then we could have problems getting finality because, I don't know, there's a lot of different reasons you wouldn't want one node to be overwhelming. But what's pretty cool is this is arbitrary. You can create the Gini and Lorentz, Gini coefficient and Lorentz curves on any arbitrary field. We have a simple macro where you just put in the name of the field here and it'll calculate the Lorentz curve and the Gini coefficient. So like literally any of this information, I wouldn't really, like you could, how many peers are connected, you could just put in peers here and it'll automatically calculate all that. Yeah, and so we detailed this out on our blog. It was a lot of fun, and that's it.
That's a very impressive project and dashboard. Can you tell us how I can get the dashboard on my wall?
If I unmute myself. Yeah, so everything we did was using the data that's out there and Splunk. You can download the free version of Splunk. We put some information in, I'm not sharing my screen. Anyway, we put some information in the blog post. There's a Docker Compose example where you can start getting all the data off of, I think, by whatever Ethereum compatible network you want to connect to. And it'd be cool to collaborate and build these dashboards together. Like it's just like JSON and XML, and the whole community could run their own instances looking at the data, setting up alerts too. So like you can automatically send alerts to Slack, Discord, mobile phone, email, based on whatever happens.
And I'll be honest, as an end user, I'm not obsessed with collecting all that data locally, but I am very interested in being able to pull up that display and seeing the health of the network in a snapshot without having to do all of the labor of managing the back end. So that's really exciting to me.
We just released the ability to publish dashboards. So we're publishing one here. If you go to MDC, Medalla Data Challenge, that's Splunk DLT, you'll actually have access to that dashboard. And it drills down into our live instance. So once you click on this, it's not like you're going to get a login prompt. But yeah, the community can build and publish these down too.
Sure. And you know, again, as a home user, this is really what I would like to mount a screen to the wall and just have up all the time, just so I can wake up in the morning and see how things are going. So
yeah, and I want to do that specifically like with my nodes that are staking too. I want to know a lot of information about my nodes, like are they being attacked or are they being offline, or lots of invalid login attempts. Or even the service, maybe I'm using some sort of staking service and I could monitor them.
How did you guys get the count for the Prism nodes and the Lighthouse nodes? Because I think you showed statistics
that
about.
was from ETH2 stats, right?
Ah, okay.
That wasn't a crawler.
Okay.
That is correct. We also crawled, but with this not been released and with the new version of Discovery v5, we're not able to crawl right now. But we did crawl. We found up to something like 800 nodes over a period of time, but that is not a definite number because you can have nodes that would come out and come back into the network. Happy to pass on to you our CSV with the nodes we found.
Yeah, because we have a similar product or website where you can see the nodes, and it was not working properly. That's why I'm asking. Yeah, that was.
All right, well, it was great. Thanks for presenting, guys. Next up, we have Elias, who works for Bison Trails, and Sid, who works for CoinBase. They'll be presenting eth2data.github.io. So with that, go ahead and take it, guys.
Thank you, Michael, and thank you, everybody. Let me just try and share my screen here. All right, here we go. Oh, can everybody see? Or not really?
I don't think so yet.
I can't see your screen.
Give me a sec. Okay. Sid, can you try and pull it up on your end? Because I'm getting
Yeah, let's see if this works.
Yep.
Can you guys see?
Yep.
Great.
Awesome. All right. So I'll kick us off, then Sid will take over for the first section, and then I'll close it off with the rest of it. So I'm Elias. I did this work with Sid. We had worked in the past together when Sid was running the token analyst. He was getting data out of blockchains. I was doing analysis and so on. So we saw the challenge being posted and felt that it'd be a good time to kind of like drum up the old token analyst spirits and attack it together. Super fun, great experience doing it, and a super great opportunity for us to kind of like learn more about the inner workings of ETH2 and how the whole system comes together. And kind of starting out, we wanted to kind of do something fairly comprehensive that kind of both merges and addresses to an audience that is not so familiar with ETH2 and kind of tells a story through data of what happened in Medalla, but also to kind of having that broad overview to maybe try and find kind of points where we can really add value either through new metrics or uncovering things that were not visible at first glance. So I'll pass it on to Sid to walk us through the first kind of pieces of our research, and then I'll take it back on.
Yeah, thanks, Elias. Yeah, just as a short intro, my name is Sid. I currently work at blockchain research at CoinBase, and it was an absolute pleasure working with Elias to dig into some of this data. Shout out to Buta and the Beacon Chain team too for providing us a lot of this data so that we could get the ball rolling. So, I mean, as mentioned before, initially our goal was to run all the major node clients and essentially get a picture of how they performed, and also pull data from them in order to actually do this analysis. However, we found out that feat was quite extensive, mainly because the node clients had a slightly different data sets when we took samples, and just formatting them into a normalized format for analysis is in and of itself quite a feat. So it proved to be pretty challenging. However, we did see in terms of performance. So just for context, we ran all Lighthouse, Prism, Nimbus, and Teku on pretty large instances, VMs on Google Cloud, where we also ran a Geth node on the same VM in order to make it as close to a optimized validator setup as possible, and saw that Lighthouse was by far the fastest sync in terms of sync times. And we didn't notice anything substantial in terms of differences between memory or CPU usage from our trials. So just that was a short takeaway from our experience with the different clients. And we'll go more into depth in terms of the clients when we discuss grouping. So this was part of our analysis that we really tried to hone in on. Essentially, we wanted to get a perspective of who is actually participating in the testnet at the given point in time, and what are the types of entities that are running validators. And so there are several points of data on chain and off chain that we could use to group validators together into clusters or into entities. Starting with the validator index, aka it's the equivalent of the public key for the validator, the withdrawal credentials, which is essentially related
to that validator index, which can be used to withdraw and can be mapped to multiple validator indexes. And then the ETH1 deposit address. That was another data point that we used where if an ETH1 deposit address deposited into the contract and could then be mapped to potentially multiple validator keys as well. And then finally, with the POAP rewards that came with broadcasting graffiti for signaling what kind of node client you are running, that was also a very helpful indicator for us to essentially use graffiti to target and label what kind of node client a person may be running. So we used all these different factors, and we were essentially able to cluster together validators into different sets of groupings. One set was what types of clients were they running. As you know, a lot of you already know, a majority of the clients that we were able to tag were running Prism, followed by Lighthouse, and then some of the others. And then additionally, you know, perhaps more interestingly, we were able to kind of narrow down the groupings in terms of what type of entity they were into largely around 22 groups. And so these kind of spread out between staking as a service firms, you know, infrastructure providers, Ethereum Foundation, several names that you can see in the pie chart here. If you can, if it's visible for you, you kind of pop out where it's like distinctly identifiable as, you know, belonging to a certain group. And these were effectively being, you know, mapped to multiple validator indexes, which could then be derived to represent what their performance was, how did they behave on chain, how do they attest, how do they vote, and how do they propose. And all of that is stuff that we dug into, and Elias will go into in more depth later on. So grouping was a big part of it. And big picture, I mean, all in, we took in the network as a whole to see, you know, when it was healthy and when it's not, what's normal and abnormal in terms of, we provided a definition where if 3/4 of the block slots available were proposed, we essentially deemed it as a normal network condition. And, you know, one of the key takeaways for us through this time, as some of you may know, there are kind of two periods of abnormality, one between, you know, epochs 2000 to 4000 during the rough time incident, and then around epoch 13,000, 13,400, where essentially both of these periods were marked by client syncing issues, you know, with you know, with Prism in the first rough time incident, and then in the second one around epoch 13,000 with Nimbus. And so that seems to have been, from our data set, the kind of led to the majority of proposer slashings, where all the slashings that we saw were attributed to double votes and not exactly to some of the other qualities, such as like for surrounding voting, that are responsible for slashing. So that was an interesting takeaway in terms of big picture. And in terms of network health, we also defined a series of different metrics to essentially define network health. As you can see in the first graph, you know, missed over proposed blocks, there's these distinct two periods between 2000 to 4000. And then in 13,000, where you see the orange bit dip a little bit, there's kind of abnormal outlier periods. And then in the second graph, we wanted to map out finality. So finality is defined as essentially when 2/3 of, you know, of the active validators essentially are included on chain. The line over here you see is what we defined as a finality threshold. And then we essentially mapped the lags, the distance, the epoch lags for when active validator votes were included on chain to essentially see what's the threshold and you know, how efficient was the network as a whole in terms of including valuable attestations on chain. And this graph really gives us a big picture view, especially during the rough time incident. You can see, you know, a significant dip there where, you know, less than 15% of the finality threshold was, you know, included on chain. So it was very interesting to see. And then finally, yes, aggregate inclusion delay. So when, you know, it's essentially mapping out this inclusion lag over time across epochs. So these are some of the big picture metrics we use to derive network health. But then perhaps more interestingly, Elias can dig into some of the, you know, attestation specific metrics.
Super, thank you, Sid. So the next bit that we took a look at was the performance of aggregation. We wanted to get into the P2P layer, but quickly realized that given time and so on, we wouldn't have enough time to crawl a meaningful sample out of it. And so we then went on chain and disaggregated a bunch of grouped attestations to figure out what actually is going on. And we found that there, over the course of Medalla, apparently, according to twice as many active validators per epoch, were included. So twice as many attestations were included on chain as activated or active validators per epoch. And this visualization here on attestations included versus active validators kind of shows you how that panned out. Over time, we initially called it attestations bloat, but then kind of like, we discussed it with various people in the community. Perhaps it's a little bit too aggressive as a term, and so we called it surplus. But then, we didn't have a lot of time to get into actually why that's happening and whether that's bad or not, because some of it, like Danny described before, is totally expected. But we did a little bit more research. Some of the results we've recently published on the Bison Trails blog, and we actually found that there's a lot of singles being included on chain, calling singles attestations that are composed of only one validator index that target the same slot, that arrived at the same time, and yet they were still included as multiple different attestations. And in fact, we found that the mean was around 22. Only looking at a sample of the first 1,500 epochs, which, as you can see here, kind of like the surplus situation was a little bit exaggerated, but you can extrapolate what that means for the rest of the testnet by looking at kind of the surplus that we observed here in aggregate. Let's go for the next slide. Sid, are you with me? Thank you. All right. We also looked at proposer effectiveness and trying to figure out how to best sort of score a validator for how well they perform as a proposer. We understand that roughly kind of for every one time, so the rewards from being a proposer are about like an eighth, or between an eighth and a tenth of the rewards that someone stands to earn as an attester. So while it's not like a big chunk of the rewards that a validator should expect, it's actually pretty important, because on kind of like the nominal per unit basis, the proposer reward is actually significantly larger than each of the attester rewards. And we kind of came up with a methodology wanting to control for both the time active in the testnet and also the probability of proposing at least once, kind of trying to capture a little bit of the difficulty with more validators having entered the testnet over time, and came up with kind of an interesting methodology, which you can find in the report. And then through that kind of blowing out one of the findings, when we segmented by client type, we found that roughly while the in the slots proposed per validator, the client sort of distribution was very similar to what we observed on aggregate. When we looked at slots missed, we actually found a higher proportion of Nimbus and Lighthouse validators being exposed to missed slots. Let's go to the next slide. We also looked at attester effectiveness and kind of tried to simplify things a little bit here of how one goes about, scoring for attester effectiveness. And we thought that kind of looking at the aggregate inclusion delay over an attester's lifetime and the uptime ratio is probably kind of the easiest and more dense in information way to come up with a metric like that, with uptime being sort of the moderator of how many times you participate in attestations, the maximum number being one every epoch for which you're active, and the aggregate inclusion delay being the moderator of how much of the max rewards you stand to get as a validator. So the longer you take to get your vote included, the less of a vote you get. And these are the results here. We also looked at the valuable to non-valuable attestations ratio. So how many surplus attestations each of the validators got included on chain. I've got this crossed out here because we're not entirely convinced that this should be a performance metric for an attester, because the fact that there's surplus attestations could be one, some of them are totally benign and expected. Two, some of them, it's probably not the mistake of or probable cause doesn't go back to the validator node, but maybe the aggregator or maybe the proposer. But we included that for reference to just like create a little bit more of a richer data set. And this is what our results look like. So a lot of people, it being a testnet and not having real money at stake, you see that there's a very highly disproportionate segment of ineffective attesters, and then like a roughly normal distribution with still quite a few laggards and actually quite a few standout performers. Next slide. And then we also kind of mapped how the score mapped against the performance on rewards. We only had data available for kind of the performance of a validator index overall in the testnet, and as such, we only in this view we only took the first 20K validators that were active on Genesis, so that we have a clear and not biased view. And we found that it's actually a pretty good predictor, about 85% correlation and so on. I think we have one more slide. And then we also segmented by client type on the attester effectiveness score, and also all the other scores like for uptime ratio and for inclusion lag and so on, and found that Prism and Lighthouse are probably the most popular clients for a reason. And then when looking at the client distribution among the top 30 operator groups, so kind of going through the same exercise, but instead of taking clients, we took the operator groups that Sid talked about earlier. We found that kind of the crushing majority, at least from the 1/3 of the whole that we were able to map to client choice, where we're using Prism. Thank you. That's us.
Yeah, I don't really have a question, but I just wanted to ask you or tell you from the community side if you could do the same thing after a month after we launched on the mainnet, because yeah, since we had so many issues on the testnets and so many releases, the data is not meaningful is not the correct word, but I think there will be more valuable on the mainnet, and if you could do that, that would be great.
Sure thing. And by the way, like all our code or most of our code is on GitHub. So if you go to our submission, there's a link that links out to a repo with all the notebooks and all the raw data for anyone that wants to kind of like take modules or replicate the analysis and so on. But we're more than happy to go take a look again.
Yeah, maybe one question. How did you guys get the client types, the Prism and the Lighthouse? Probably from the Graffiti, or? All right, okay.
Yeah, basically from the Graffiti was the main source, from the POAP identification from the Graffiti.
Okay. Yeah, many people cheated on that, so.
Yeah, I'm sure.
I mean, it's still valuable data.
Yeah, thanks.
No, I'm not saying that the data is not meaningful. I'm just saying the fact that people have cheated, but in combination with other stuff like the uptime. So if someone had a Lodestar Graffiti and didn't have any, or wasn't in the, or if someone has a Lighthouse client and uses a Prism, graffiti and we know for a fact that the Prism uptime is very high, the likelihood of him cheating is very high, if that makes sense. I can repeat if you want me to.
Yeah, I think I get what you're saying. We tried to group it where it's not just graffiti wasn't just the only characteristics, but also other things, right?
Yeah.
Like validator, withdrawal keys, public keys, ETH1 public keys, so on and so forth. So there were cases where we saw guys trying to spoof where they just put random POAPs on their graffiti just to try to get rewards. So tried to exclude those from the analysis.
I think it's the case of when there's no perfect data available, you use the best thing you can and try to make sense of it. And I think you all did a really good job of that. So
yeah, so even we as Explorer had wrong data, so I'm not blaming you guys at all. I know it's hard.
Thanks.
We know. It took us like two or 3 days to get like the correct data out again. But props to you for kind of being super responsive and on top of this.
Yeah, so we had, since we only had one client running, which was Prism, there was no chance for us to actually backtest it with a different client, but that will change soon with the new API, with the standard API. And then I think all the challenges and all the analysis will be more accurate.
all right, thank you all very much. For our next presentation, we have block data. You can find them at blockdata.github.io. We have Gurdal Ertek from the Sloan Kettering Cancer Center in New York, USA. So we're looking forward to hearing from you all. They have 3 consecutive presentations.
Yes. Can you see this? Can everybody see the screen and hear me correctly?
Yep.
Yeah.
Yes,
all
I
right.
can see and hear.
All right. Everybody, welcome to our presentation. And this is for the Medalla Data Challenge, and this is our analysis by our team. Our team consists of 2 members. I'm Gurdal Ertek, and I'm a business professor at College of Business and Economics at UAE University in Abu Dhabi, United Arab Emirates. And Joseph Kholodenko is a data engineer at Memorial Sloan Kettering Cancer Center in New York. And we will be presenting our 3 articles here, articles 01, 002, and 003. So those are the 3 articles that we will be presenting. So what are those articles? The first article is about the Ethereum 2 beacon block. So this is a visual documentation of the Ethereum 2.0 beacon block, which is basically the most important the block on a most important chain in Ethereum 2.0. So that's our first article. And then our second article is analysis of data propagation latencies. And our third analysis is clustering and profiling of time epochs in Ethereum 2.0. So again, this is our team. And we'd like to thank everyone in the community and everyone who helped us as well for this project. So yeah, let's start with the first one, and I'll try to finish each one of them in about 5 minutes. So I'll try to finish everything in about 15 minutes. All right, so what is the first research? What's the first article? What's our first contribution? The Ethereum 2.0 beacon block, a data schema and visual documentation. So what we did here was we provided a visual documentation, and even more important than the documentation itself, we came up with a way of documenting such blockchains. And so it's not only the specific documentation that we did for ETH 2.0, but the generic methodology that we developed, which can be applied to pretty much any blockchain. So our focus is the beacon chain and a block on the beacon chain. So the chain, of course, consists of blocks. So we focus on data on a single block, and we focus on the data rather than the metadata rather than the data itself. So rather than the whole data, we focus on what is the data structure, what is the data schema. And since a picture is worth 1,000 words, our approach was visualizations, and especially interactive visualizations. The first one is a 3D visualization of architecture. The second one is data schema diagram, again, interactive visualization. And the third one is a zoomable presentation. And we did the documentation using a DBML, database markup language, using actual data from Medalla. So when we look at the content, the first one is this three-dimensional visualization of the architecture. So it's, it enables you to zoom in, zoom out, and then play with it, so you can just see and focus on areas that you're interested in. Okay, so of course this could be used for visualizing any blockchain's architecture. The second one here is the interactive database schema, and we also put some simple instructions. So you just click on the image and hold over fields and links. So you can just hold over the links, and then so you can see the relationship between the different fields, or you can also look at the relationship between the specific tables. And this is on the left hand side, this is the DBML code right there. Okay, so that's the second interactive visualization, and you can focus, and then you can look into specific things. All right, and the third one is is a zoomable presentation that we created using Prezi. Of course, we used, as you can see, we used the screenshot from the earlier one. So here, this is the interactive visualization. So let's maximize this, and now we just it just focuses on every single component of the data, and it also provides actual data. As you can see, it provides actual data from the Medalla Testnet as well. All right, so the beacon block, proposer slashings, and then all the other different components, different areas of data tables, the groups of tables. All right, so those are the three visualizations. And then later in our paper, of course, we also went into the detail of each one of them. So for each table, we describe what is in each table, and then for each one of them also we provided the database structure, including one-to-one mappings and many-to-one mapping and other one-to-many mappings, and then also actual data from Medalla Testnet. All right, so that was our first contribution, and our goal here was to flatten the learning curve. Many people, developers, auditors, validators, data engineers, and scientists, they need to learn about ETH2, and how can we make it easier to learn? There is wonderful documentation out there, and can we just make that documentation easier to digest, if you will, through the understanding of metadata? And this, I believe, as far as we could tell, this was the first time that we have seen all these different approaches being used to describe metadata in a blockchain through interactive visualizations, and it's applicable to any blockchain. All right, so that was our first contribution. Now, our second contribution is an analysis of data propagation latencies, delays, basically, in the Ethereum 2 Medalla Testnet. And here we applied not only visual methods, but we complement the visual methods with formal statistical analysis. Because, especially if we're talking about, let's say, differences, okay, let's say we have one group of one sample and we have another sample, and the means are different. But then if one of them has a higher mean than the other one, is that really, just when we look at the averages, is that a conclusive answer? No, we need to do statistical analysis, because the difference may be due to some statistical variation, due to the randomness. Okay, so that's why statistical analysis is important in our opinion. That's why we implemented that, and then we came up with some actionable insights as well. So we started with the Medalla Testnet data, and Mr. Jim McDonald kindly shared that with us. And it was a PostgreSQL dump, and we basically had some SQL queries, and we went through certain steps, and eventually we obtained these data fields. And we defined inclusion distance for each slot as the maximum inclusion distance over all attestation aggregations and over all committees that participated in the voting for that slot. So this is more like equivalent to maximum inclusion distance. Now we know that in some of the other entries for the data challenge, the definition is different, even though the term is the same. So this is our specific definition of the term, and it is actually a metric for delays in the system. Okay, but then even if one prefers another definition, the methodology that we will present is still applicable to that other definition of the metric as well. So we start with univariate analysis, and then we had a distribution of average inclusion delay, and the average inclusion delay, it's of course it's a bit skewed because there's an upper limit, right? There's an upper limit of 32. So this, by the way, what is this 32? This is the number of slots. Okay, so this is number of slots, but then this is per epoch. So per epoch, what is the average inclusion delay in terms of slots? And now we have a similar histogram and a distribution fit for the number of missing blocks as well. And it turns out the software we use suggested that beta distribution would be a good fit for both of these. All right. And next analysis was looking into correlations, because correlation will motivate us to come up with the hypotheses and to see which pairs of variables, which pairs of attributes would be interesting to analyze together. And here we immediately see the higher values here, here, here. So those are definitely worth investigating. All right, and when the first analysis that we had was, the next analysis we had was patterns over time. So over epochs. Now, again, when we're measuring inclusion distance, the inclusion distance is measured in terms of slots, but then the analysis that we have is over epochs. And as our colleagues earlier mentioned, we removed any data from before epoch 5000 because of the mentioned problems in the system, in the blockchain network. But then we focused on anything after epoch 5000. Of course, we couldn't include the latest one because we were still working on the data at that time. We already had the data plot down. So one of the analysis that we did was voluntary exits. How many voluntary exits do we have in each epoch? Now, the maximum number is 22. And then we also see that there are no exits, and then boom, suddenly there is like a narrow time interval where there are many voluntary exits. So what's happening there? Especially, it's very obvious here, right? In such a short, in a few epochs, so many voluntary exits happen. So what is that? What's happening there? Again, we don't know what happened, but this is something that points us to that direction. Now, the first conclusion that we get actually is that the average versus standard deviation of attestation inclusion distance are inversely associated, as we have this, as we can see from the scatter plot. When we plot the inclusion distance standard deviation against inclusion distance average, we see immediately the inverse relationship. Oops, sorry, I couldn't draw very well. So, okay, let's try again. Okay, yeah, there's the inverse relationship. And of course, the software we used also gave us a nice fit for a polynomial function. So we could express the relation as such as well. All right. Then the second, another analysis, which gives us our second result, is inclusion distance versus committee size. Okay, so again, inclusion distance, basically propagation delay. How does it change with respect to the number of committees? And then turns out it first decreases and then it increases. Okay, now again, coming back, are these statistically significant differences or not? To that end, there's a well-known test in statistics called Toulme test. And this will allow us to make multiple comparisons. And there is Bonferroni, I think this is, yeah, there's a Bonferroni inequality that we also use to come up with the correct alpha values. Anyhow, to return back to the practical aspects. So there's a difference, as you can see, it seems to change over number of committees. So depending on the number of committees, the inclusion distance seems to be affected. But is this statistically supported? And the answer is yes. So, for example, what does this mean? This table gives us the results of the Toulme chart, and we also visualize the table over here. So what this says is this. For example, whenever the number of committees is 256, which is this case, the mean inclusion distance average is higher than 288, and yes, it's statistically supported. So 1 means it's statistically supported. If it's a pink one, it means it's less than, but it's still statistically supported. But what about the difference between this and this, for example? So here it's 0, so it's not statistically supported, even though there's a difference. So since this table is a bit hard to read, we applied a methodology that I mean we had developed with another group of researchers. I was part of that research team. We visualized it as a graph, and we had a hierarchical layout. So this tells us that whenever the committee size was 352, and let's just calculate what that means. So committee size over an epoch being 352 means, and there are 32 slots in an epoch. So that means if in a slot the number of committees in that slot was 11, that was the lowest inclusion delay. So that's when the propagation delay was the minimal. Now, this is not saying that the committee size should be 11, because why? Because the committee size, the number of committees, the number of committees should be 11. Is it saying that? No, because the number of committees, the committee size, the epoch, they are all related to each other. But this is definitely telling us this committee size is associated with average inclusion distance. And another result that we obtained was with regards to voluntary exits. So whenever we observe voluntary exits, okay, so if the voluntary exit is not 0, but if it's greater than 0, so we observe that inclusion distance average is higher, right? It's higher than the average. So we did formal statistical test. First, we tested for parametric. We tested for normality, and we decided not to use parametric test. And then eventually we applied Mann-Whitney test to come up with a p-value of less than 0.01. So basically what this says is voluntary exits are positively associated with average inclusion distance. In other words, if there are voluntary exits in an epoch, there will be more propagation delay. All right, why is this important? Again, it helps us understand on-chain data. We adapted formal statistical methods to this domain. And also, we also came up with a software stack. I mean, all these analyses, they were not done, only with Python or R. We used many different software, and we also provide definitions and descriptions in a very concise manner. And again, the methodology is applicable to other metrics and other on-chain data as well. Now, the third analysis is clustering and profiling of time epochs. So here, the clustering is on time epochs, not the validators. And we both cluster them and we profile them. So our goal is something like this. Remember the 4 seasons of Vivaldi. So now we have the 7 seasons of Medalla. And we again applied visual and statistical analysis, interactive 3-dimensional clusters. And then basically we found that there are unique clusters of time epochs, and these clusters can be profiled, and there are many implications for future research. How many clusters should we have? We came up with that using the silhouette score, and the best number was 9, but then eventually we used 7 because some of the clusters had too few observations. So, and then we have an interactive visualization, which you can go ahead and analyze. You can just interactively analyze how the clusters are mapped in these 3 dimensions. And then we also analyzed these clusters, we profile these clusters with respect to each other. And then we see that, for example, cluster 2 has the highest inclusion distance, and that is statistically significant. Here also you can see that. And then it also has the highest number of attester slashings, and then second highest number of mean voluntary exits. And then, so this is basically, this cluster of time epochs is where there are significant issues. All right. So this is the first research of its kind that, to the best of our knowledge, because we used machine learning of unsupervised machine learning and combined it with formal statistical analysis for time epochs. That's what it makes it different, and it opens many issues. So what did we learn from this whole project? Number 1, cancel everything during the datathon because you're not going to be able to find time for anything else. Set up validator nodes on your own. Don't wait for data from others because you may never get it, but eventually we were very lucky and we got it. So engage in ETH Staker Discord channel, share ideas, share data, share everything, publish early on your results so you get feedback, and ask people. Don't be shy and ask for ready data. There are amazing people who are ready to provide that data, just as in our case, Mr. Jim McDonald did that. And understand architecture, mechanics, and metadata first, rather than jumping into analysis. This is what we will tell to ourselves in the future. Okay, start small and then increase in the analytics maturity. Target visual analytics first, and use a toolbox rather than a single tool of Python, because implementing everything in Python may be too much time consuming. And the data tone basically calls for frugal data science. So here are the slides that support these lessons learned. These are the stages of analytics maturity as suggested by Gartner. And then this is which visualization can be used in what type of situations and what type of purposes. And this is a more comprehensive one. And then this is the software stack that we used for our second analysis, and the third analysis was also similar. And this is frugal data science. Again, it's best to apply these principles in data tones, which we did. And this is also one of my working papers with a colleague. So hopefully we'll submit this soon. All right, that's all. Thank you so much. And that's all from from our side. Thank you so much for listening to us. Thank you.
Wow, nice. Thank you. First of all, where can I find the slides?
Slides, please drop me an email and we'd be happy to. I'd be very happy to share. My email is my first and last name with no space, no dot, nothing @gmail.com.
Okay.
And we are planning to put it on the internet. For now, though, I can at least share with you on email. Yeah.
All right. Yeah, like the part where you talked about the inclusion distance versus the committee size was something I wanted to do with my team, but we had no time. But I think, I'm not sure if you talked about it or if you mentioned it at all, but do you see a correlation of specific validators? So I have to go back a little bit. So the attestations themselves, I'm pretty sure they're also referred as the shards that we are going to see in the future. So the shards that we are going to have in phase one. So the one committee is representing one shard. And if we have those shards in each of the epochs, is there any correlation of having a bad inclusion distance if you are always in committee one? Does it mean that committee one and committee one has a bad inclusion distance? Is there a correlation between the inclusion distance and the committee, or is it correlated to the validators?
Okay, I think it's as far as we could tell. Again, we learned everything in these 40 days. We didn't know anything about Ethereum 2. We just dived into it and we tried learning how to swim. So the way we understand is that the assignment of validators to the committees is random. Okay. So I mean, it's not something related to the index of the committee, but it could be the number of committees. How many committees are in each slot. That could have an effect also, especially when it comes to ETH2 phase one, when the shard chains are being introduced. Yeah, that's definitely the analysis that we implemented here. It could definitely be used for that. I mean, it's important to look into number, but then again, not only the number of committees, but also the committee size and the epoch. So maybe that was down because something else happened in the epoch, not necessarily due to the committee size, right?
Yeah, I think we had to dig a bit deeper. So if a specific validator is always causing a bad inclusion distance, that goes way deeper. But yeah, thank you.
Sure. Thank you for the question. Thank you, Sam. And thank you for your help, by the way. During those 40 days and nights, you were one of those who helped us answering our questions. Thank you. Buta ETH, right?
Yeah, thank you. No problem.
Thank you.
I do have a question, and this kind of goes out to all of the teams, really. Through all of the work and the dashboards that everyone has created, was there ever any point where you guys, the teams, were like, whoa, that's really neat, or something unexpected happened? Were there any of those moments at all?
Yeah, sure. For example, I mean, I was personally very impressed with the other submissions and what they did, and the depth of analysis, the interesting insights. That was especially, I was very impressed with Splunk's dashboard, because I'm coming from a PMS. I also have this side, PMS, performance management systems. So I really like that dashboard. It was very interesting, very rich.
Thank you. Yeah, we had a lot of fun. Our team likes to do our offsites at places like ETH Denver, and we haven't been able to get together for a while. So I said, let's spend a few days and let's just do a hackathon. This Medalla Data Challenge is perfect timing for us. So we just sat down, learned a lot, and had a lot of fun. And a surprising thing for us was, as we were building that operations center dashboard, we started seeing the health score go down. And we're like, what's going on? And we were sure our searches were broken or something. And then we ended up finding out, and then my Prism node crashed a little bit later. Anyway, it was just really fun that it was the perfect time for us to do this hackathon, because that's when the network started having issues. So that was a really fun, cool surprise. One thing we wished we had done was, we were really excited about Rumor, which I just put in the the chat, but we didn't have the time to get it going to the level that we wanted to, but that looked a pretty cool way to get a lot more data.
Yeah, we thanks to everybody, actually. Like all the submissions were great, and we also kind of like learned a lot from everybody else. The most surprising thing that I think that we found was the surplus attestations, or what we called surplus attestations, or what seemed like surplus attestations. So, our prior kind of coming to look at the data was that we would find approximately like as many attestations as validators active in every epoch. And actually what we found was that it was, towards the later stages, when the network normalized a little bit, was that it was twice the number, right? And kind of like that raised an eyebrow, because okay, we started like talking to the community and reading docs and reading the research and so on. And we realized that, okay, some of it is to be expected by merit of how the BLS signatures and the aggregated proofs work. But then also it seems like 2x was actually pretty high, without having any yardstick to compare against, right? Or like a really objective rule. And so we're still playing around with a bunch of data and kind of like trying to figure out what the actual sort of truth is there, and like getting even more granular into figuring out, what types of events lead to that result.
All right. Do any other of the teams or moderators have anything before we kind of close up here?
Yeah, I want to say it was really nice to have things like Beacon Chain out there to really like investigate whether what we were building was working and was right. And so thank you, Buddha.
Thank you so much. Very nice experience. Thank you.
Awesome. Well, before we close up here, for those of you who tune in and are watching this on a recording, we do want to ask to subscribe to the ETHStaker YouTube page by searching for ETHStaker, all one word, on YouTube. By subscribing, in addition to being notifying when the ETHStaker community posts new content, it also helps us with YouTube feature sets, like being able to stream live events in the future. So to support the ETHStaker community, please consider subscribing to the ETHStaker channel today. Also, if you're ever overwhelmed by the speed of Ethereum news and want to learn more about events and programs like Ethereum Study Master or the collaboration groups, or just information in general, all of that and more can be found at the ETHStaker Reddit community at reddit.com/r/ETHStaker. Also, our ETHStaker Discord server at invite.gg/ETHStaker. We're just a group of exuberantly friendly people who are passionate about Ethereum. We welcome all ability levels to join our community to learn and have fun. So with that, I personally want to thank all the teams for one, joining this call and presenting everything, but two, doing this actual work. Extending off of Superfizz's comment, as an end user, this stuff is incredibly exciting because we can sort of remove the layer of abstraction that is Ethereum and put it into these real data sets and visual representations. And I think it really humanizes the network and it makes it more fun. It gets more people involved that aren't just end users, that they're data scientists, they're people that maybe don't have the knowledge or skill sets to develop these tools, but they know how to analyze the data that the tools represent. And I think that's incredibly great and powerful for our community at large to help mature and get to those next steps. So thank you very, very much for the time and hard work and dedication that all of you have put in for this. And I think with that,
thanks everyone.
Yeah. Go ahead.
Thanks for coming out.
Yep. Thank you
everyone,
very much.
Take care.
And,
all right.
Have a good one.
Bye-bye.
Thanks.